let's retrace our steps in the derivation of the dragging versus diffusion equation. The current is equal to the conductivity times E plus velocity of plasma cross B. Lorentz force law. This is already a simplification. Right, notice the instantaneous generation of current due to fields. And this, we eventually got to dB by dt, the way the magnetic field changes in time, as due to two competing terms. One we call the dragging of the field with the plasma, and then there's a diffusive term that involves the tangling up of the field. This will decrease the field if it becomes high enough. And another simplification that we haven't really discussed in any detail is that this velocity, this one velocity, so there's one fluid here, there's one current, one fluid, and really we should be careful distinguishing between positive and negatively charged particles. But in the MHD, in the magnetohydrodynamic approximation, we think of it as one fluid. That's probably something that breaks down near black holes. And then we mentioned that as the conductivity increases to the point that it becomes infinite, but we still have finite currents, right? So this is finite. So it must follow that this quantity goes to zero, so that 0 times infinity can be something finite. So this goes to 0 as this goes to infinity. And when we do a transformation in relativity, you can see that this kind of a quantity is just the electric field in the frame that's moving with this velocity v. So it's the proper electric field, and the proper electric field therefore must be 0 because the conductivity is effectively infinite. And when we do this, we end up getting the flux freezing condition, right? That this is just due to the first term. Okay, so we saw how this implied the magnetic flux is frozen into the plasma that's moving with velocity v. And so what this means is that the magnetic field gets essentially, right, again, we have a black hole here. We have an accretion disk of material rotating around the black hole. We'll look at the mathematics of that later on. But this material is rotating around and moving closer in. So it has a small radial velocity component and a large angular velocity component. But overall, this means that that magnetic field gets brought in toward the black hole. And you can sort of see that this field gets all tangled up eventually. So if the field gets tangled up, that sort of speaks to this term. So what we're saying is that this term starts to increase, and if it increases dramatically, right, it can go to infinity as you, in an unconstrained way, allow the field to be completely tangled up. So what do we make, if that's the case, what do we make of this term? What does that become? Okay, you can't really truly model that kind of a thing on a computer because the computer involves finite differences. Sorry, the equations involve finite differences. And so you can't really approximate the continuum. You can't really model the continuum. So you're limited in what you can do with this kind of a thing. But there is a sense in which we don't need to worry about this because there's something called turbulence that somehow comes to the rescue. And the idea is we can just, so you just put this mathematics into a computer, and then the field starts to get tangled up, and the computer, it gets tangled up in a way that sort of forces the computer to break down. It's something called numerical diffusion. So numerical diffusion. The computer can only handle so much tangling up, and you'll get magnetic fields. So maybe we can make a drawing. Magnetic field in some region, right? So the plasma is moving around, it's tangling up the field. Here's a field line, let's say that's going up like this, and then it starts to get dragged around like this. Over here, it gets twisted all up like that, let's say, and then eventually you'll get, because of this numerical diffusion, you'll get a realignment of the field. So you'll get, this thing will kind of break up because you have too much energy in this configuration, and it'll end up with, say, this becoming part of another field line, and this side becoming part of another field line. And these can go off in some other direction, right? This continues as well. Divergence of B is always 0. So something like that happens. You've realigned the field. And so the idea is you don't really have to worry about the term that has this inverse conductivity or resistivity, because your simulation your computer simulation doesn't need to track this in any detail, because numerical diffusion comes to the rescue. The problem is that there's energy in this configuration, and there's a lower energy in this kind of a configuration. So where did the energy go? Okay, so the energy, what's going on with the energy? That energy that goes from the magnetic field configuration to something else, how is that tracked? Right? There's no equation here that deals with that kind of a thing, because we have the simplification. And so the energy has to go to particles, to the charged particles in some way. And this is sort of all kind of put in by hand. And so we can say that it's unlikely that the current state-of-the-art in numerical simulations is really capturing reality, especially near a black hole.